And happy Saturday, and welcome to Diagnostic Review. We're going to talk about the chemistry and physics section of your diagnostic test and help you make sense out of some of what's there, and also help you learn how to apply some really important skills to taking tests. Well, happy Saturday to you too, Rosa. So I want to make sure that you can see and hear me, so if you can give me a quick AV check down there in the chat, just so that I know everybody's on board and that we're all set to go. And what we're going to talk about, Mike had mentioned this when we were out in the lobby. We do have several other teachers here in the classroom, by the way. My name's Rebecca. We have Mike and we have Paul, who are available to answer questions for you. We also have Kristen, who's doing some behind-the-scenes stuff, but they're all also available to help out. Now, we're not going to be going over every single question in the chemistry and physics section of the diagnostic. Why not? Well, let's think about this. It took 95 minutes to take that portion of the test. If we're going to review it, it's going to take us an hour and a half to actually sometimes as much as 3 hours. So that isn't practical. What we're going to do instead is pick and choose some really important aspects of the diagnostic and look at how those are applied on a much broader level to important things you need to know for the test. Now, should you go back over the diagnostic yourself? Absolutely. You want to make sure that you review the questions you got wrong to find out why you got them wrong, and you want to review the questions you got right to make sure you got them right for the right reason. But this should help with that entire approach. All right, so let's take a look at what we're going to cover today. We have 3 goals. The first thing is, all right, these are big words. Efficiently extract information from quantitatively themed visuals. What? How to read graphs and charts to get the right information out of them. That's all that means. Then we're going to take a look at questions that you find associated with passages that really aren't about the passage. They may be on the same topic, but they require specific external information. And we're going to talk about some of the external information that it's very important for you to know for test day. And then finally, we're also going to take a look at what we call discrete questions. Discrete questions are the ones that aren't associated with a passage at all. Now, something you may notice, might not have had the chance to figure it out yet, those discrete questions are usually easier than the passage-based questions. So those are really good ones for building your confidence, getting yourself warmed up on test day. So we're going to also take a look at those and figure out which ones are just content-based and some of the important content you need to know. So let's start with this first one. Let's take a look at graphs and charts and how we figure out what those mean. Also, we're also going to be looking at some formulas as well. All right, so what we're going to start with here, this is the first passage you encounter. Now, we're going to come back and take a look at the passage as a whole in a few minutes, but right now, let's just focus in on this equation and this chart. Now, tell me down in the chat, what did you think when you first looked at this equation? Even looking at it now, what kind of a response do you have to this? Is this something that looks really straightforward, like, oh yay, I can hardly wait to drop some numbers into this and do a calculation with this equation? What did you think when you saw it on test day? Good, bad, or indifferent? Seems straightforward, but does it look like something that's going to be very fun to calculate? Not really. The numbers aren't round, it's not warm and fuzzy, and we have a chart down here that goes with it, our table 1. Now, table 1, the difficulty with a table like this is you're trying to figure out, do I need to know about this or not? Now, typically, tables and charts make for really good question material on the MCAT. Most of the time. We're going to see a case in a few minutes where that isn't necessarily true. But what you don't want to do is you don't want to spend a lot of time on these calculations, on these equations, or on these tables right up front. So instead, we just want to say, okay, what is this table? It's a bunch of blood gas measurements for one patient. We're given a whole bunch of values that match things that were talked about in the passage that we may or may not need to use at some point. So, equation 1, we are told, based on the label and in the passage, it's a measure of oxygen content, and table 1, list of blood variables for that patient. Okay? So, let's take a look at a question. Question number 1 is asking for the oxygen content of the patient's blood. Well, isn't that what equation 1 is? It's the oxygen content equation. And it's asking for things like hemoglobin levels and SO2 levels that are given from the table. So we've actually got a plan right here that we can use equation 1 and plug some numbers in. So what do we plug in? Values from the table. This is straightforward so far until we start to really mess with this equation. Because when we look at the equation, oh, these are not fun numbers. We've got these numbers that are going to be difficult to calculate. Why? Tell me down in the chat. What don't you get on this test? What do they not provide you with? It's an important tool. We're all used to using it. Yeah, there's no calculator. So looking at these numbers, it can be, oh my gosh, this is not going to be any fun. So that's why we need to look at this equation carefully and see if we can make some sense out of it. What we're going to do is first look at the second half of the equation. Why? Because the second half of the equation means we're going to multiply a number, 95 millimeters, that's the PO2 from the table, by 0.003. Now, tell me what's going to happen when we multiply by a number as tiny as 0.003. What are we thinking about that final term in this equation? Exactly, Amit. You got it. It's going to be negligible. So we are not even going to worry about this. All of a sudden, we're doing half the calculations that we had to before. All right, that just made our life a lot easier. So when we plug these numbers in, this won't even matter. But the first part, those, again, not warm-friendly numbers that we want to cuddle up with, unless we think about them not as, all right, I have to multiply these out, but what can I figure out about these numbers? What do we do with 0.99? What do we do with that right there to make our lives a whole lot easier immediately? Yeah, that's going to be just 1. Okay, that was a lot easier. But now we have to do this 1.34 times 13.5. That's really the only part of this calculation that matters. Now, you can multiply it out. You can make a little multiplication chart and go through it and spend some time on it and worry, did I do that correctly? Or we can stop and think about it. If this were 1 times, and I'm not even going to use 13.4, if it were 1 times 13, what would it equal? This is not a trick question, by the way. What do we get with 1 by 13? We get 13. What's 2 times 13? What would we get in that case? We would get 26. At this point, we are done, because we know the answer has to be between 13 and 26. And if the answer is between 13 and 26, what is the only possible answer? Is it A? Is it that close to 1? Yeah, it's going to be B. It's answer choice B, because it's got to be significantly bigger than 13. Why? Because it's 1.3. If we've been thought in terms of 1.5, 14 is really close to where we are already, because it's really 13.5. This is going to be too small. But we want the number that's about halfway in between, and by far the closest is the 18. So again, think about the numbers logically, and don't just pick the first one you see because, oh, A works. Now, make sure you check the other numbers out. But did we have to do any complicated math for this? Did we have to write out 1.34 times 13.5? No, you want to think smart. That's exactly right, Rosa. That's how you want to approach calculations on the MCAT. And here's the thing. The MCAT, they know you don't have a calculator. They're not trying to be cruel, despite what you might think about the MCAT. Instead, they want to know, can you think logically? Can you figure out how to make something that looks difficult easier to do? They want to select the test takers that can figure out how to do this. So when you get to a complicated calculation, ask yourself, there's got to be some way to make this simpler, or it would not be on this test. All right, very nice. Now, let's take a look at passage number 2. Passage number 2, we've got some stuff going on with the enzymes here. And again, we have some equations and we have another figure. Now, one thing about this figure, are there any numbers on this graph at all? Any numbers associated with this graph in any way? No, it's all just relationships. So that's what we're going to be looking for with this graph. Not actual results or values. We're going to be looking at relationships. And so when we look at this graph quickly, we're going to try to figure out things, okay, it's linear. And linear is important because it means we have a slope associated with it that we can figure out. And they tell us, in fact, what the slope and the intercept are here. And always make sure you understand the axes. 1 over s down here. Okay, if we look down at the bottom, we have our 1 over s is our substrate, right? And 1 over v is 1 over our reaction rate. V is a velocity of the reaction, and that means the reaction rate. Okay? This is all pretty much classic enzyme kinetics, and you're expected to be familiar with it. You don't have to have this stuff memorized, but familiarity is going to help you out here. And we're also given that the slope is dependent on 2 things, Km and Vmax. But what's the difference between those two? What's the relationship to Km for our slope? How would you characterize that relationship? Looking at the equation for it, is it direct or inverse to the K sub m? Is this direct or inverse? If our K sub m increases, what happens to our slope? Yeah, that's direct, exactly. But what's the relationship to Vmax? There you go. That's inverse. Very good. And that's the sort of thing you want to establish very quickly. You don't want to spend a lot of time on this, but understanding if something is a direct relationship or an inverse relationship actually gets tested a lot on the MCAT. So that's definitely something that we're going to want to know. Okay? The y-intercept, there it is. Notice it tells us where it occurs. Well, the 0, that's this 0 here, but it occurs at 1 over Vmax. Again, very important piece of information, but not something we spend a huge amount of time on. It's just something we want to make sure we glance at, get that in only a few seconds of looking at this chart. So now we are given 2 more graphs. These are not the same as the one we looked at because now we have a second line added. So the first one looks directly like the graph we saw. What's the first one labeled as that's important for us to notice right away? What's the label on the top graph that gives us important information? Yeah, it's competitive inhibition, so that we want to notice that. And what do we notice when we add our competitive inhibitor, our dashed line? What things change on our graph? Something changes. Yeah, very good, Oriel. The slope. Very good, Ibrahim. So the slope is increased, but take a look at the intercept. No change there at all. If we compare that with our non-competitive inhibition, once again, we get an increase in slope, but is our intercept the same anymore? Yeah, the intercept has changed, and it's larger with the inhibitor. So these are the sorts of things that we want to make sure we quickly understand. Again, without a lot of numbers, we can't do more than establish these relationships. And if something changes, what else changes along with it? That's part of relationships. And then we have this table. Okay, now this table has a lot of information in it, but we start by looking at what's going across the top. Okay, or actually, we actually start with the caption. So we have reaction rates with and without a non-competitive inhibitor. So first we have our substrate concentration, then we have a column that says without the inhibitor, and then a column with the inhibitor. So what happens in general as we increase substrate concentration without an inhibitor? What relationship do we quickly notice? It's the without inhibitor column as we increase our substrate concentration. What do we quickly see? Yeah, we increase our rate. Okay? Also, if we have the inhibitor present, we still increase our rate, don't we? But what relationship do we see for V without the inhibitor versus V with the inhibitor? For the same substrate concentration, what do we notice? It's a slower rate. Very good, Ibrahim. And there's something else we can very quickly establish. Very good, Connor. It's exactly half. Okay? Now, here's the thing. Do we want to spend a lot of time on this graph and figure out exact numbers, or do we just want to look for trends? In this case, Any extra time, any time we spent more than that would be a waste. Why? Because in this particular passage, there are no questions on this graph. It's just thrown in there as additional information. So if we spend a huge amount of time on this particular table, not going to get anything out of it. On the other hand, it can be helpful. We never know, so it's always worthwhile to very quickly review the graphs and tables. Okay, so now let's take a look at the actual questions that were asked. Now in this question, apparently from where? Oh, it tells us where to look, figure 2. And it's asking what's happening with competitive inhibition. Now, we got some important information out of this, didn't we? We figured out that for competitive inhibition, the y-intercept is the same, but the slope increased. If the y-intercept is the same, what is it's 1 over V max. That means 2 of our answer choices at this point we can throw out. Which 2 answer choices are already gone without doing any more work than we've already done? What are we able to determine? Because there's definitely something that's gone here. If 1 over V max hasn't changed, there's something else that hasn't changed. If 1 over V max didn't change, what else are we absolutely certain didn't change? Very good. Ibrahim's got it. C and D are gone. Because if 1 over V max didn't change, V max didn't change, right? If the inverse of something doesn't change, that number has to stay the same. The next thing, we're going to take a look at, since the other 2 answers are about K sub M, we need to figure out that. But what is our slope? What was the definition of our slope? It's not just K sub M. Very good, Ibrahim. It's K sub M over V max. But what do we know is true of V max? Well, V max, we just decided, doesn't change, right? So any difference in slope is due only to what changing. If the slope changed, what absolutely had to change? The K sub M. And if our slope increased, what else do we know about K sub M? It increased. So what answer choice is the only one possible at this point? Yeah, very good, Daniela. Very good, Rosa. It has to be answer choice A. So again, even without numbers, we're asked to figure out these relationships between the different variables and how they affect the graph. And this is very common. The MCAT loves to give you graphs with slopes like this and make sure you understand these relationships. Very, very common thing to be questioned. All right, excellent. Now, let's take a look at our next learning goal. So far, we've been answering questions based on information given to us in the passage, but often we're going to run across questions associated with the passage that don't use information from the passage. Instead, you've got to pull information out of your brain. Well, that means you have to put that information in your brain. And there's a very common misconception about the MCAT. I've seen students make this mistake in the past. They hear the first half of a statement, which is that the MCAT does not usually reward memorization. And students stop listening at that point and say, great, I don't need to memorize anything. The second half is you do still have to know information. There are things you are going to have to memorize for this test. Very rarely are you going to find questions that are pure content regurgitation. There are a few, and you want to make sure you get them. You still have to learn the content to be able to understand other parts of the test as well. So memorization goes a long way. Actually, before we get into this passage, so how do you memorize things? How do you learn formulas? How do you learn amino acid structure? How do you remember all the different types of hormones in the endocrine system? What are some techniques you can use just for getting that information firmly implanted in your brain? What do you like to use? What have you found that's successful? Tell me a few things. Mnemonics. I'm a big fan of mnemonics. Absolutely. And if I don't have a mnemonic for something, I will make one up, which is a little scary because some of mine are really silly and stupid and cheesy. But you know what? Cheesy mnemonics make it easy. Okay? Yep, Rosa, absolutely. You have to memorize those equations. How else can you memorize? if you've got a whole bunch of equations that you have to learn, say for physics, what are some tools you can use to learn all those equations, for example? What might work? There are some tools we give you, as a matter of fact. So what might you be able to use to do that? Deriving equations, okay, that can help, but you know, Abraham, that can go a long way back. You can use the units to make sure you have them right. Connor's got it. We give you a wonderful flashcard app. And I know flashcards seem really grade school, but you know what? They work really well. And even though we give you this fantastic flashcard app, I will tell you, the best flashcards that you can come up with are the ones you write down yourself. And the reason is that the act of writing down information helps you to remember it. So either the flashcard app or self-made, this is really helpful because you don't have to study them. You just use them as a quick review. Do I know this or not? If you know it, it goes in the I know it pile. If you kind of sort of know it, it goes in the I need to work on this pile. And if you've never seen it before, it goes on the wow, do I need to work on this pile. The other thing you can do, this is a really handy thing. The more you see information, the more that you're going to retain it. So you can use sticky notes, or you can use even whiteboard markers and put them up on mirrors, put them up on doors, put them where you're going to see them. Write on your bathroom mirror with dry erase markers. Why? Because as you're standing there brushing your teeth, really, are any of us not bored when we brush our teeth? Okay? You're going to be staring at information and learning it. So give yourself the chance to learn this type of information in a more effortless way. You're standing in line at the grocery store, you pick the wrong line, don't you hate that? And you know if you change lines, the one you change to is going to slow down. Pull out some flashcards and flip through them. Really important to do. All right, let's apply this. Let's go back to the beginning of passage 1. Now, passage 1 has a ton of information in it, and it's really easy to get lost in this information. So we need to make sure we're looking at the right stuff in this passage. And this passage, the first paragraph, doesn't look like it has very much information in it, does it? Okay, measuring blood, it's complicated, and okay. The last sentence of paragraph 1 is your best friend. Why? This is a typical structure. You'll see it maybe in about a third and maybe up to a half of passages. The last sentence of the first paragraph gives us what I call a table of contents. It says there are 3 important things. Now, important is a keyword. Most important is even more important. Because if the author says it's important, shouldn't we think it's important? Yeah. And what things does the author say is important? Well, let's see. Oxygen pressure, oxygen saturation, and total oxygen content. Now, why do we care about this? We care about this because if the author put them there in that order at the end of paragraph 1, what do we think is going to happen in the rest of the passage? What's going to happen going forward? What do we think we're going to find? Since he said these are the 3 most important things, what's likely to show up here? He's going to explain them, and he's going to explain them in what order? What order are they going to be given to us in? And this is like at 90% true, since he said in that order. Oxygen pressure, oxygen saturation, and total oxygen content. Yeah, you know what you've got? You've got your labels for the next 3 paragraphs already done, given to you by the end of the first paragraph. Do not overlook this. This is really critical information that makes this passageway easier. So one of the things we know about the next paragraph is not the order of how important they are, it's the order they'll be given. So we start with the discussion of oxygen pressure. Okay. And on oxygen pressure, we've got this electrode, which is one scary-looking figure, yeah, okay. And it talks about the total amount of oxygen in the blood that we're measuring, and then it gives us one more thing. And let me talk about highlighting for a moment. Highlighting is a feature you have on the MCAT. You have the ability to go in and highlight information in the passage. But highlighting is like hot sauce. Now, I love hot sauce. I put hot sauce on my food all the time. But what happens if you take your bottle of Tabasco or Cholula or Frank's Red Hot and you dump it all over your entire dinner? What happens if you dump that hot sauce, the whole bottle, you know, the little plastic thing that slows down the flow pops off and bloosh? It ruins the food. If you highlight too much in the passage, it's not going to do you any good. You're not going to be able to pull out the important information. But there is something that you should always highlight. And the thing you should always highlight, numbers. Why is it important to highlight those numbers? Why is that such a critical thing to do when you're going through this passage? What should you be anticipating when you see a number like that? Exactly, Rosa. You got it, Emma. Exactly, Mohit. You need to be able to go back to them for calculations, and you don't want to be digging around in the passage looking for them. If you highlight the numbers, they're going to pop right out when you need to find them. And this is a number in voltage, isn't it? Oh, so why do they make you study physics for the MCAT? Doesn't that seem unfair? Nope, not at all. This is a way that physics is applying directly to something medical. So it's very important that you understand physics. That's right, physics is life. My theory is that all biology is biochemistry, all biochemistry is organic chemistry, all organic chemistry is chemistry, and all chemistry ultimately is physics. So all you need to study is physics, right? Wouldn't that make life easier? Or maybe even harder. Okay. Let's take a look at the second half of this. We started with O2 pressure. Now we're going to do oxygen saturation. And we have an interesting word, words in italics. Again, might be something you want to make note of. When it's italicized, that puts emphasis on it. That means it's important. Our third paragraph, surprise, surprise, total oxygen content. And this is what we saw before with all of our equations and our table that goes along with it as well. So this is how to pull out important information. Let's see how we can use this to answer a question. Well, actually, the iron atom and hemoglobin combine to 6 different atoms. All right, there was a little bit about hemoglobin in the passage. One of those atoms is a nitrogen atom in histidine. Was histidine mentioned anywhere in the passage? Did they actually talk about amino acids? No, they did not. So what's this question really asking about? It's asking about histidine, and it's asking what its side chain is. Now, if it's not in the passage, how are you going to answer this? How do you answer a question like this where there's nothing in the passage that's going to help us out? General knowledge. Although I wouldn't say this is general knowledge, Rosa. That is correct. It's actually specific knowledge, isn't it? Histidine's not mentioned. You are going to have to know your amino acids. Okay? So what does that mean? It means you need to at least know what group each amino acid falls into, whether it's polar or nonpolar, acidic or basic. You want to know your aromatics versus your non-aromatics because it's all testable. And having a general idea of properties is important as well. Do you want to necessarily memorize every single one? Probably not, but there are important ones you do need to know. Cystine's important, glycine's important, proline's important. Here, oops, and I managed to pop up the answer before I planned to. Oh, the answer popped up early there, sorry. Histidine is one of the aromatics. Okay? That's what you want to know about it. And that, again, flashcards, put things up on that mirror, put sticky notes everywhere in your life, put them inside other books where you don't expect to see them. But you have to learn this information in order to get, these are some of the more straightforward points on the test. You want to make sure you get these. All right, how about this next one? What's important about this particular question? What do you notice about this question that makes it significant? The units, okay, it's in ohms. And it's giving us amperage, right? But there was nothing about this in the passage. Nothing in there at all. What was the only thing in the passage that relates to this question? What's the only thing in the passage that possibly has anything to do with it? Yeah, that voltage. Remember I said to highlight that voltage? Yeah, and to do this problem, we need to know something. We need to know the relationship between voltage, current, and resistance. So what gives us, what formula, and this is an important one, you definitely need to have this one memorized. Mohit's got it, Ohm's law, V equals IR. And you know what, as far as electrostatics and circuits go, this is one of the more straightforward formulas to know, and it's one that you will definitely. There are a few things that can be guaranteed on test day. If your MCAT doesn't have an application of Ohm's law on it, then you are allowed to email me and tell me that I was dead wrong. But I would bet money, well, okay, let's not bet money, let's bet cookies. We'll bet cookies that you see Ohm's law on test day. Tell me what kind of cookie. Actually, I like chocolate. Anything with chocolate. So you can send me cookies after test day. All right, so, and virtual cookies are fine. So, we've got current. We've got to get that value of voltage. Remember, we highlighted it. That's our 0.7 volts. And then we put that into Ohm's law. Now, once again, we have to do a little bit of math. And unfortunately, in order to solve for resistance, we have to divide decimals. And don't you just hate that? All right, if we want our resistance, we have 0.7 divided by 0.01. Now, here's the problem. Is it easy to get totally mixed up with all of these decimals? Is that something that can make us crazy? Absolutely. So here are two different ways you can approach it. One is you can put both of them into scientific notation. If you're comfortable with that, what you're going to get is 7 times 10 to the minus 1 over 1 times 10 to the minus 2. What are you going to get? Be careful with your scientific notation here. Be very careful with this because you have to subtract -2. Emma's got the other approach. That's right. Here we're going to get 7 times 10 to the -1 plus 2 is to the first, which gives us 70. Now, what Emma said is absolutely right. One of the other things we can do is take our 0.7 over 0.001 and multiply so that 0.01 becomes 1. Well, how many decimal places did I move? I moved 2 to do that. So what do I have to do with my decimal place on top? You got to move it by 2 places. And that gives us 70 over 1. Either of these techniques will work. Use the one that you're more comfortable with. But again, don't get intimidated by the decimals. Just turn it into a form that makes it easy to do it right. Okay? And the answer is indeed answer choice C, 70 ohms. Okay. Very nicely done on this so far. You're catching on very quickly, and being able to do these math skills, super important. All right, this one doesn't have anything to do with math. Yay! But notice it's really long. On the other hand, do we see a pattern in our answer choices? Looking at our answer choices, any pattern that's there that's going to help us out. What are we noticing? Well, there's an order to them. What word appears in every one of our answer choices? Variable. And notice this is about dependent versus independent versus confounding variable. I don't think that's a real thing. Okay, so this is asking about experimental design. Knowing that, we've got our researcher who wishes to study the effects of replacing a mouse's hemoglobin with leg hemoglobin, a hemoprotein that has a very high affinity for oxygen, okay, whatever, by comparing that mouse's PO2, SO2, CO2, and blood pH to those of a normal mouse. So, what is our researcher manipulating? This was not covered in the passage at all, okay? They don't talk about independent versus dependent variables. In fact, they don't even talk about leg hemoglobin in there. They talked about the methemoglobin, but not the leg hemoglobin. So we have to use our outside knowledge to figure this out. So this is all about what's going on with these variables. Okay, so we need to define our terms. So we have something that is going to be kept the same, and then we measure everything that varies. Then we take that first thing, and so that's round 1. We measure all of the different things associated with it. Then we switch that to something else, say 1 is our control and 2 is our experiment, and we measure the same things. So our PO2, our SO2, and our CO2 are what we're measuring. We're changing from a normal mouse to our leg hemoglobin mouse. So what are we changing? The dependent variable, the independent variable, the control variable, or the confounding variable? Which one is being changed here? What is the researcher manipulating? Now think about what the words mean. Dependent variables change based on what an initial variable is. If we go from normal to leg hemoglobin, our dependent variables, PO2, SO2, and CO2 change. So what is the original 1 or 2 in here? Yeah, it's the independent variable. That's the definition that we're being given here. The independent variable affects the results of the dependent variables. In other words, the values for PO2, SO2, and CO2 depend upon whether it's normal or leg hemoglobin. So the ones that we get, our results, PO2, SO2, and CO2, depend upon whether it's a normal mouse or the leg hemoglobin mouse. Because they depend on which mouse, they are dependent variables. The independent variable is one that we set up and then measure the things that depend on it. Does that make sense, Olivia? And again, there's information in your books. This is covered a lot in the psych and sociology session. Well, the independent, yeah, you're manipulating the independent variable to see how the dependent variables, the things that depend on it, change. Okay? All right. So let's take a look at something different. Let's move on to a different passage about a different topic. Let's look at passage 3 instead. We kind of beat passage 1 to death here. Passage 3 is very interesting because it talks about sound. And when we look at sound, for the most part, this is going to be studied not so much in chemistry and physics or even in biology. This is a matter of perception. And so perception is going to be covered very much in the psychology and sociology section of the test. But this is one of these instances where we can see how sound also can be tested as a physics property. So here, we're given first the structure of the ear, all the part, the malleus incus and stapes that transfer the motion. Then we have the cochlea, which is our liquid-filled tube. And then this is bisected by the basilar membrane. And this is all the biology of it, right? Then we start getting into musical instruments. Wow, okay, that's different. With our musical instruments, we're going to be looking at how a drum works. Like the tympanic membrane, it vibrates. All right? So now we're getting lots of different membranes, and then we get let me try that sentence over again. Then we get an equation. And the equation, you will notice, is pretty complicated looking. What does this equation measure? Now, it's told to us in the paragraph. This is one of the great things. If you get a brand new equation you've never seen before, they will always tell you what it is and what the units are. Yeah, it measures frequency. And it measures frequency related to a bunch of other stuff. What's defined for us are the T, which is the tension, R is the radius, sigma is a mass, F is relative frequency. They describe all of the different variables that go in here. And then we get to our third paragraph, and now things get really weird. We've got these modes, and they depend on M and N. But what we are told is M has something to do with diameter, N has something to do with circle, and we're given a figure that shows modes of vibration. Does any of this look familiar? Anything here that you have ever seen before? Yep, this is all confusing. So what do you do if it's confusing? Do you sit here and try to figure out what's going on with it? Is there any point to doing that at all? No. Say, you know what? I'm not going to let this sucker me into wasting time on this. If I need to answer a question about any of this, I'm going to come back to it. But for right now, I'm going to move on and see if there are points that I can pick up. Okay, so now we get to question number 12. What do you notice about question number 12 when you just look at it, when you just glance at it? What are your thoughts about this question? Warm, fuzzy, wow, I can hardly wait to do this. It's long, there are units involved. Yep, they gave us some information at the end. And what do we notice about our answer choices when we look at those? They're in seconds, and they're short numbers, aren't they? They're nice little short numbers, and, you know, they're all relatively, they're not really that close together. It's like we have multiples of 6 here. 6, 11, 18, 23 is close to adding 6 to it each time. Okay, that's going to help us. And this is about somebody falling from free fall. Was there anything about this in this passage? Anything even remotely related to this? Now, this is not a passage-based question at all. All right, free fall, we've encountered this. This is very much physics, okay? So it says the initial difference between our outer and middle ear is 0. That's the only thing that seems to relate to the passage right now. If the pressure in the middle ear remains constant while the outer ear equilibrates with atmospheric pressure, then how long would it take for the person's eardrum to rupture? Oh, joy, doesn't that sound like fun? And then they tell us how much pressure the eardrum can sustain and the density of air. What did you think about this when you looked at this? What were your thoughts on solving this problem? How many of you said, oh joy, what a wonderful, fun problem to work on? What did you think when you ran into this? Not at all. Rosa said, not happening, okay? And Rosa, that's not a bad decision. This type of question is becoming much rarer on the MCAT, but there are still a handful of them on the test. You're going to need to use an equation to figure this out. But the challenge of this question is that it's actually a two-part calculation. You have to first calculate how far does this person have to fall before the pressure gets to 8 times 10 to the third pascals, and then you have to figure out how long did it take them to fall that distance. So that's the challenge. It's not just a single calculation, it's a two-part calculation. And these, honestly, are the questions you want to leave for last because they do take a lot of figuring out and they take a lot of time. So, exactly, Connor. So let's look at how we would do it. The first thing we have to do, let's say you've done everything else in the section and you're going to come back now and figure it out. First thing we have to figure out, all right, what does it take to increase the pressure to 8 times 10 to the third pascals so that this eardrum, boom, ouch, ruptures? Well, the difference in pressure is given by this. You may recognize this, you may not recognize this. This is gauge pressure. Rho is density, G is our friend acceleration due to gravity, and delta H is how far this person has to fall before the pressure becomes too large. So we're solving actually for delta H. So we're going to take our change in pressure, our 8 times 10 to the third pascals, and we're going to divide it by our density, and we're going to round that to 1.3. Really, you're not going to, even the 1.3 is, we're going to see in a moment, isn't that big a deal, times gravity. Now, what happens with this? This is no fun. We have 8 times 10 to the third over 1.3 times 10. Now, what's the logical first thing to do? Let's get rid of that, and let's turn that into a 2. So now we're looking at 8 times 10 squared divided by 1.3. Let's just deal with 8 divided by 1.3. What's 8 divided by 1? Not a trick question. What's 8 divided by 1? 8. Very good, Rosa. And what's 8 if we divided it by 2? Also not a trick question. It's 4. Well, since it's 8 divided by a number that's roughly halfway between 1 and 2, how about if we estimate and use 6? Oh, okay. That's a lot easier than setting up and calculating 8 divided by 1.3. It's 6 times 10 squared, which is going to give us 600. And this is supposed to be 10 to the third right there. Okay? And I'm not even going to worry about 615. I'm just going to use 600 meters. That's only the first half of the problem. Now we have to figure out how long does it take to fall that far. Well, for that we use our TAX, T-A-X. T-A-X has time, acceleration, and distance. And yes, you need to know these kinematic equations for absolutely sure. Okay, we've got our delta H, we're solving for T. But what do we know about how fast was this person moving when they started? How fast were they moving when they started? Yep, Rosa, we're only halfway through so far. They started at 0. Well, the good news is that means that V initial times T is 0. That makes our life a whole lot easier. So now we want to solve for T. T is going to equal, or T squared is going to equal our delta H divided by 2A. All right, which is 600 divided by 20. I got something wrong there. That's not the right number. What did I miss? Oh, the 2 delta A. Yep, the 2 goes up top. Okay. 2 times 600 divided by 10. Thank you. See? See how easy it is to make these mistakes? How many times do you think I've done this problem? Managed to get it wrong. All right, excellent. So this is going to be 1200 divided by 10, which equals 120. Now, that's T squared. So T has to equal the square root of 120. Now, there's a problem here. 120 isn't a perfect square, but it's pretty darn close to something that is. What's the correct value of T here? Yeah, you can round it down to 10, or you can round it up to 121. The answer is going to be somewhere around 10 or 11 seconds, which is which answer choice? What's the only possible answer choice here? Yeah, it's answer choice B. On the other hand, is this problem worth it for a first pass on the test? Any way at all that you want to do this thing, first time around? No, you want to be smart. Go get your easy points first, then come back and do these calculations. And yeah, there are still going to be a couple of them, but make sure that you get the ones, the critical reasoning questions, the ones that you can pop through really fast. All right, we've talked about a lot of passage-based questions. I want to move us on to our third learning goal, learning goal 3, because learning goal 3 is what about these questions that are not even associated with the passage at all. The last set that we did, Mike had mentioned in the chat, these are what we call pseudo-discrete questions, when they're included with the passage but don't use information from the passage. But this test also has completely discrete questions that don't use anything from the passage at all. Let's take a look at just one or two of these. Let's start with question number 22. Now, again, what we're looking at here, the question's kind of long. Answer choices are really long, but since it's discrete, let's see if we can figure something out here. All right, the Ka2 value for carbonic acid is smaller than the Ka1 value because once the first hydrogen is removed from the carbonic acid, well, okay, we need to know a couple things here, don't we? First of all, carbonic acid. Carbonic acid is really important because it is this. It's H2CO3. And when carbonic acid dissociates, when it goes through its first dissociation, we get an H+, and we get a super important molecule. Anybody know what this molecule is right here? Talk about something that's going to show up on test day. What is that molecule? You should recognize it because I guarantee you're going to be tested on it. Very good, Rosa. It's bicarbonate. Bicarbonate can be tested all over the place. It can be tested in Gen Chem for acids and bases. In biology, it's a blood buffer. It transports CO2 through the blood. It shows up in the digestive system to buffer stomach contents when they move into the small intestine. Just like, say, Ohm's law, I said you can be pretty certain you're going to be tested on that. You can be darn certain you're going to be tested on bicarbonate, one way or another on test day. Now, this is our first equilibrium. There's a second equilibrium, which is where our HCO3- also dissociates into another H+, and CO3 2-. Okay, that's what the Ka1 and Ka2 are talking about. These are simply equilibrium constants for this dissociation. All right, it's saying that the Ka2 value is higher for the second dissociation than for the first, and they want to know why. Well, what does that mean? It means that second proton is harder to remove. A higher Ka2 value, a lower Ka2, remember this is an equilibrium constant. A high equilibrium constant means the reaction wants to go forward. It favors reactants. A lower equilibrium constant says, nah, not so eager to go forward. So why is the second proton harder to remove? This is very much critical reasoning. Looking at our molecules here, why do you think it's harder to pull off the second proton? Why is that second reaction harder to make it go forward? Just looking at the molecule should give you the answer. Nope, it's not about stability. The negative charge, Ibrahim, you're on the right track. Keep going. What about the negative charge? What do we know about our bicarbonate already? And Ibrahim, you're right there. There's something about that negative charge. Yeah, Oriel, that's right. It would much rather get a hydrogen back than give up another one. It's already got a negative charge, so that proton really wants to hang around. And if we try to pull that proton away, now we're making it a -2. Yeah, so which of our answer choices says that? Which of our answer choices actually tells us it's because the proton doesn't want to leave? Yeah, exactly. Answer choice A. Okay? So do you need to know anything about Kas? No, but you should know carbonic acid and bicarbonate. That's really important to know. It's a great molecule to make sure you have information on. Okay, let's do one final question. I love this question because it comes back to a point I made earlier. Let's jump forward to question number 14. Why do I love this question? Because it's another application of physics to biology. In fact, scary, horrible physics, electrostatics. Electrostatics, just as important to know, because you know what? Happens all over the body that we're talking about potentials and fields, and it's especially important here. It's asking what contributes most significantly to the negative resting membrane potential of neurons. Okay, so what's the question really asking? Why do neurons have this negative resting membrane potential? Now, what do we know about how neurons work? What kinds of things create charge differences in a neuron? Sodium and potassium. Exactly. Tell me more, Emma. What about sodium and potassium? Exactly, Oriel. There's something very specific about it. The pump. Yeah, it's all about the sodium potassium pump. So this, let's make sense out of it. What happens with the sodium potassium pump? Very good, Daniela. You anticipated what I was going to ask. We said 3 sodiums out, but only 2 potassiums come in. And what does that mean happens? Excellent, Olivia. Yeah, excellent. It's more negative on the inside, Ibrahim. That is exactly right. And that brings us to answer choice A. There you go. So it's actually thinking very rationally, very clearly about what's happening with membrane potential. Don't get all frozen up, oh my gosh, that ugly word potential and that physics stuff. It actually makes sense in terms of the biology and what you know about the biology. All right, very nice job. I hope that you learned a lot about how to manipulate math, how to deal with a lot of these types of questions on this section of the test. Also remember that you've got pseudo-discretes that may be related to the topic but don't come from the passage, and do not forget to scoop up the points on the stand-alone discrete questions themselves. This was a lot of fun. This is a smart group. I'm really pleased with how you did on our questions today. Make sure, very good, Daniela, recognizing relationships and graphs is a critical thing to do. Make sure you look at the rest of the questions on your diagnostic. You always want to study both right and wrong questions to see what more you can learn from them. Oh, you're welcome. Thank you. I'm so glad you were here. Have a great rest of your day. You may want to stick around for the next session. Kristen's going to teach the next section of our test. Excellent, Emma. I'm glad you're getting a lot out of it. We love having Channel available for you. Okay, have a great rest of your Saturday. Study hard and do great on your MCAT.